Imagine you're looking down. The water beneath you is black. Not dark, black. The kind of black that has weight to it. Temperature sensors on research vessels in the Antarctic record water so cold it sits just above the threshold of freezing. Not because ice hasn't formed, but because the salt won't let it. The ocean here doesn't want to become ice. It wants to stay liquid. It wants to stay alive. Now imagine something moves down there. Not fast, not the darting panic of a fish. Something slow and enormous, drifting through the dark like a thought you can't quite shake. You can't see what it is. You don't know how far down it is. You don't know how big. That feeling, that specific unease, is the right place to start this story. Because what lives in the coldest water on Earth doesn't just survive the cold, it uses it. The cold builds these creatures. It feeds them, expands them, sculpts them into something that shouldn't be possible by any intuitive logic. Cold water, by all conventional wisdom, should produce smaller animals, less energy available, slower systems, harsher conditions. Smaller is safer, smaller is practical. Except in the polar oceans, the rules are inverted. Here, the cold doesn't shrink life, it enlarges it. This is the central strangeness, the contradiction that marine biologists have been pulling at for over a century. When you think about cold environments on land, a tundra, a high-altitude forest, you see creatures under pressure. Small bodies, compact forms, everything conserved. Evolution in the cold is usually an exercise in minimalism. But drop beneath the surface of the Southern Ocean or the icy waters of the Arctic, and the logic flips entirely. Down here, cold is not the enemy of scale. Cold is the engine of it. The phenomenon has a name: polar gigantism. And once you understand the mechanism behind it, you'll never look at cold water the same way again. Let's talk about what actually lives down there, because the theory only lands when you see what it produces. The colossal squid, Mesona hamiltoni, is not the giant squid of mythology. It is something worse, larger, heavier, built like a slow-moving nightmare in the deep. The largest confirmed specimen measured over 14 feet and weighed nearly 500 kilograms. Its eyes are the largest of any known animal, dinner plate wide, designed to catch the faintest traces of bioluminescence in permanent darkness. It lives in the Southern Ocean, in cold so profound that human divers cannot reach it without machinery. It does not chase its prey. It barely needs to. It waits, and the ocean delivers. Then there are the Antarctic sea spiders. On land, sea spiders, pycnogonids, are small enough to sit on your fingernail. In the Antarctic, they grow to the size of a dinner plate with legs that span over 30 centimeters. They move with an alien slowness across the seafloor, absorbing oxygen directly through their skin because their bodies are too large for any internal respiratory system to keep up with. They are ancient in design, unchanged for hundreds of millions of years, and the cold has made them vast. Antarctic starfish grow to sizes that would be extraordinary anywhere else on the planet. Colonies of them carpet the seafloor in the Ross Sea, some individuals reaching over half a meter in diameter. They are not passive decorations. They are slow, methodical predators. Some species capable of engulfing prey far larger than seems reasonable for something with no brain, no eyes, and no urgency whatsoever. The lion's mane jellyfish, found in the cold North Atlantic and Arctic, holds the record for the longest animal ever documented. Its bell can stretch over 2 meters wide. Its tentacles trail more than 36 meters behind it, longer than a blue whale. It drifts through the water column like a living city, a tangle of stinging filaments that can span an area the size of a tennis court. It does not pursue. It exists, and things swim into it, and they die. And then there is something that sounds almost mundane by comparison: Antarctic plankton. Specifically the copepods and krill that form the base of the Southern Ocean's food web. They are not glamorous, but they are enormous by the standards of their kind. Many Antarctic copepod species are several times larger than their temperate water counterparts. In polar seas, even the microscopic decides to go big. So why? What is the cold actually doing to these animals? The answer starts with oxygen. Cold water holds more dissolved oxygen than warm water. This is basic chemistry. Gas dissolves more readily into colder liquid. The Antarctic and Arctic oceans are therefore among the most oxygen-rich environments on Earth. And oxygen, for an aquatic animal, is not a comfort. It is the fundamental currency of cellular function. More oxygen available in the water means more oxygen absorbed, which means more energy available, which means bodies can afford to grow larger without suffocating under their own metabolic demands. Now layer the second mechanism on top of that, metabolic rate. In cold conditions, the biochemistry of life slows down. Enzymes work more slowly. Cellular processes take longer. This sounds like a disadvantage, and on land, it often is. But in the ocean, a slower metabolism means a more efficient one. An Antarctic sea spider doesn't need to eat very much because it isn't burning through energy quickly. It can afford to grow slowly, steadily, across decades because it isn't racing a biological clock that demands constant fuel. Large bodies, crucially, are also more metabolically efficient in the cold. Surface area scales with the square of an organism's size. Volume scales with the cube. As an animal grows larger, it loses proportionally less heat through its surface and requires proportionally less energy to maintain its internal processes. In cold water, large is efficient, large is sustainable. Large is, paradoxically, the path of least resistance. Finally, there is environmental stability. The deep polar oceans don't change much. Temperature fluctuations are minimal. Food sources, while seasonal, are predictably enormous. The spring bloom in Antarctic waters is one of the greatest biological events on Earth. Stability allows for long-lived, slow-growing bodies. Evolution here doesn't need to produce fast, adaptable generalists. It can afford to build something slow, enormous, and extremely well-suited to a world that doesn't change. Here's where it gets more interesting, and where a common mistake gets corrected. You might be thinking, polar bears are huge, walruses are enormous. Doesn't that prove the same thing? It doesn't. And the distinction matters. Warm-blooded animals, polar bears, walruses, whales, are large in cold climates for an entirely different reason. The mechanism is called Bergmann's rule, and it operates on the same surface area to volume logic, but in reverse motivation. A larger warm-blooded body retains heat better. Less surface area relative to mass means less heat lost to the environment. For a mammal trying to maintain a constant internal temperature in the Arctic, being big is simply a better thermal strategy. Polar gigantism is not that. Polar gigantism is cold water invertebrates, animals with no internal temperature to maintain, growing large because the oxygen-rich, metabolically forgiving environment allows them to. One is about keeping heat in. The other is about the ocean giving you the resources to grow beyond your limits. They look similar from the outside. The mechanism underneath is completely different. Now here is where the story turns. Ocean temperatures are rising. Not dramatically, not by the standards of your afternoon weather report, but by the standards of a system that has been stable for millions of years. Fractions of a degree matter enormously. Warmer water holds less dissolved oxygen. This is the same chemistry running backwards. And for an animal whose entire biological strategy depends on oxygen-rich water, whose vast body was built by and for that oxygen, warming is not merely uncomfortable. It is structurally fatal. Large bodies that were once efficient become liabilities. They require more oxygen than warming water can supply. They cannot adapt quickly because their entire evolutionary history has been built around a stable environment that wasn't supposed to change. The slowness that made them successful, the decades of steady growth, the unhurried metabolism, now becomes the thing that prevents them from responding in time. There is a quiet violence in this. These are not animals that will die in dramatic, visible collapse. They will simply stop reproducing successfully. They will grow smaller, generation by generation, as the pressure of reduced oxygen slowly selects against the bodies that the cold once celebrated. The giants will retreat, not in a moment, but across decades, a slow erasure of something ancient and strange. The cold ocean has been building giants for millions of years, working with a patience that is almost incomprehensible. It's selected for size with the precision of an engineer and the timescale of geology. It produced animals that seem impossible, creatures that break your intuition about what the world should contain. What's unsettling is not that they exist, it's that their existence is conditional. That something as quiet and invisible as a few degrees of temperature change could begin to unwind what took epochs to construct. The black water is still there. The slow, enormous things are still moving through it. For now, the cold is still doing its work. But the cold is changing. And what the cold built, only the cold can keep.